Would life really develop differently on another planet? Convergent Evolution. Pointed ears, blue skin, abnormal head, or reptilian jaws. There are 1,000 ways in which science fiction, literature, movies, and alleged witnesses' accounts have depicted aliens visiting Earth. So different in height, shape, and somatic features, but still with one thing in common: a vaguely human appearance. But if in the entertainment world it is easier and cheaper to make up actors as humanoid ETs rather than as shapeless blobs or tentacled octopuses, in the scientific debate the criteria are evidently different. Yet there is still no consensus among researchers as to what these possible neighbors from the next galaxy should look like. Assuming and not assuming they exist, are they similar enough to us or so different that our minds cannot even imagine them? Try to follow along as we will try to find out together, okay? Some argue that it is futile to speculate on the nature of alien life. Our imaginations would be too constrained by our own experience to be able to embrace the amazing heterogeneity and unusual possibilities perhaps realized in other worlds. Well, if I may express my personal opinion, I disagree. In my opinion, science can help us overcome such a pessimistic view, allowing us to make realistic assumptions about how aliens might be structured morphologically. Many like me are confident that the laws of physics and chemistry are unambiguous and universal, and they work on Earth just as they do on any exoplanet. If there is one thing we know for certain about aliens, it is this: they too, just like us, are a product of evolution by natural selection. Others, however, believe that biology is an exception. They find it hard to believe that the biological laws underlying Earth's evolution are also applicable to exoplanets. Carl Sagan, one of the most famous astronomers of the 20th century, was firmly convinced that intelligent life existed elsewhere in the universe. Yet he wrote, "To our knowledge, however, biology is a literally terrestrial and provincial science, and we can be familiar with only one special case in a universe of diverse biologies." When we face the unknown, there are indeed good reasons to be cautious. But why should biology be terrestrial and provincial rather than universal? Shouldn't the laws of nature, physical, chemical, and even biological, be common to the entire universe? Fortunately, there is a strong component of scholars in the scientific community who don't think like Sagan. According to them, aliens, if they exist, cannot be so different from us. And to support this hypothesis, they usually invoke a well-known phenomenon, that of evolutionary convergence. Basically, species subjected to the same environmental pressures tend to develop by natural selection, similar to anatomical features. This is why a mammal like a dolphin looks similar to a cartilaginous fish like a shark. Even a creature that developed and lived in the liquid ocean of a distant exoplanet would probably develop a fish-like shape to move quickly. But just a moment. Before we get into the details, it will be good to clarify which aliens we are talking about. On our Earth, there are currently some 20 million different species, from the whale to the gnat. If our discussion were limited to ascertaining the differences between any animals on Earth and any animals on an extrasolar planet, well, then we would already have the answer. Indeed, one need only consider the extraordinary variety of shapes and sizes of our fauna to realize immediately that an alien planet with environmental conditions similar to our own would probably also be home to millions of species extraordinarily different from each other. There would also be animals there, large and small, terrestrial and marine, flying and terrestrial, occupying every environmental niche available. Not identical in form to terrestrial ones, but certainly similar in function, dictated by environment and evolutionary pressure. So that when we go out and actually discover a large number of Earth-like sentient worlds, we will find that most of the creatures on them took forms designed by physical and biological laws. Fish-shaped swimming organisms, bird, bat-shaped flying creatures, four-limbed turriculous creatures, and perhaps largely upright, two-armed, large-headed bipedal sentients, humanoids that use tools. It should therefore be clear that when we speak of comparisons between aliens from different planets, we must mean only morphological comparisons with sentient beings who have arrived to express a technologically advanced civilization. It matters little whether an extrasolar planet is inhabited by millions of very strange species. The point of this discussion is to answer the question, if aliens from another star system came to visit us one day, what would they look like? Hang on a sec, guys, before we continue. Be sure to join the Insane Curiosity channel. Click on the bell. You will help us to make products of even higher quality. First, a true alien would have to be bilaterally symmetrical, endothermic with excellent manipulative abilities, and have a rigid brain case. If we consider the living beings present on Earth, we realize that all the more complex ones, particularly on land, exhibit bilateral symmetry. That is, it is possible to divide the body with a sagittal plane separating two mutually specular halves. This is true for a human, as well as for a bear or a mosquito, but it is not the only possible configuration. For example, an octopus or a starfish exhibits radial symmetry. On Earth, all of the most complex organisms exhibit bilateral symmetry. The appearance of bilateral symmetry has been of enormous importance in the evolution of living beings on Earth. The earliest organisms with bilateral symmetry moved in a single direction, and this caused one end of the body to come into contact with its surroundings before the rest of the organism did. The sensory organs therefore developed on this end, because this enabled them to detect the characteristics of the environment in which one was moving sooner, and from the data from these organs to be processed more quickly. The nerve centers that perform this function needed to be as close as possible. Over time, millions and millions of years, this led to the development of a head which contains the brain and has the sense organs of sight, taste, smell, and hearing. Most scholars believed, based on what can be observed in the millions of animal species on our planet, that even a hypothetical, technologically evolved alien would exhibit some symmetry, probably bilateral. However, we must not forget, someone objects, that our evolutionary path is the result of a very long sequence of random events. So much so that if it were possible to restart from the same initial conditions thousands and thousands of times, not a single other time would this path be identical. And all the more reason that this would be valid in an environment, albeit similar, that is nonetheless alien to our own. A being developed in a distant world might therefore not have bilateral or even radial symmetry, which would obviously make it appear quite different from us. Such a creature would appear very strange and ungainly to our eyes because of how our brains evolve, but it is still possible. But this is an objection that could be answered by saying that the diversity they are talking about could only occur among lower animals, and not in a species that has been able to evolve to the point of technology. The reason is intuitable. Octopuses get by in their environment, but they certainly could not exist as land creatures. Moreover, no matter how pliant their tentacles are, they cannot manipulate objects in fine ways, an ability they did not develop because it was not necessary for the marine environment. Deciding factors would be the specific characteristics of the host planets. Earth's fauna, including humans, is absolutely determined by the history of the planet through millions of years of evolution, climate change, habitat adaptation, and mass extinctions due to external events. For example, the impact of large meteorites or the explosion of nearby supernovae. This means that even under exactly the same geographic and environmental conditions, i.e. in the case of a planet identical to Earth with the same astronomical and astrophysical characteristics, evolution could certainly have taken total, unpredictable paths, and thus capable of producing differences far greater than a pair of pointy ears, but always well within defined limits. However, there are two environmental components capable of directing the evolution of an ecosystem: gravity is a key factor influencing the development of all organisms. In addition to limiting the size of land animals, gravity also imposes several very specific adaptations. We can see evidence of this right here on Earth. Organisms that made the transition from water to land had to develop complex limbs and skeletons because they no longer had the buoyancy of water to compensate for the force of gravity. Of course, on Earth with the same gravity, there are complex living beings of all sizes, from the mosquito to the blue whale, the latter probably approaching the maximum size attainable by any animal on our planet. But there are probably limits for a technologically evolved species. To be able to process metals, for example, a creature could hardly be as small as a squirrel, just as, on the other hand, a being the size of a brontosaurus would have serious difficulty developing aircraft capable of supporting its own weight, let alone space capsules. These are just two examples of how dimensions too small or too large would constitute, if not an insurmountable limitation, at least a major break on the technological development of the species. Imagine a hypothetical situation in which Earth's gravity is doubled. Although this would not necessarily force all complex life on Earth to reassemble a squat, turtle-like creature, the likelihood of being bipedal humans would decrease dramatically. Even if we could maintain our two-legged method of movement, we would certainly be much shorter and have larger bones to accommodate the stronger force of gravity. Meanwhile, an Earth with half the gravity would probably have the opposite effect. Earth animals would require less muscle and weaker skeletons to cope with gravity, and life in general would be taller and larger. While we can't theorize about the general characteristics of life in high or low gravity, there is no way to predict more subtle adaptations. Such adaptations would further alter the appearance of alien life. The atmosphere obviously also plays a role in directing evolution. For example, arthropods that lived during Earth's Carboniferous period some 300 million years ago were significantly larger than their modern counterparts. Dragonflies nearly a meter long were running around in those days. And this was due to higher atmospheric oxygen content, up to 35% versus 21% today. And okay, all this means that similar environments developed similar forms regardless of their evolutionary history. On Earth, this is called parallel evolution. The canonical example is the mouth shape of the flamingo, which begins an almost exact replica on a small scale of the mouth shape of whales, even though they share no common history. Why? Because they are both filter feeders of microscopic organisms in the water and both have hinged jaws. That shape is the most efficient to do that job. And at that point, it's physics, not biology. If we went to another planet and found an animal with articulated jaws that eat the same way, it would have the same mouth shape. The same is true for all evolution in similar environments. The fact that the environment is on another planet is irrelevant. Final considerations. In short, for me, it goes like this. If the alien has come down to us, or at any rate possesses the means to make contact with our species, it will be of an intelligence at least equal to ours, and therefore, from an evolutionary point of view, can only be structurally very similar to us. It may be strange in all the ways you can imagine: scaly skin, number of fingers varying from 3 to 5, ridges on the head, bad ears, etc. But it will definitely be similar to us in size, symmetry, and number of limbs, upright posture, head with eyes, and openings for mouth and nose. Of course, coming down the ladder of the spaceship will not be a gelatinous telepathic blob, incapable even of using a screwdriver or tapping on computer keys. Nor will it be a cephalopod like the ones in the movie Arrivals, who took over the science of space travel by talking to each other in ink splatters. So what about you guys? Whose side are you on? Who says that an alien with technological intelligence has to be just like us? The Divergent Evolution. One of the main lines of thought in contemporary astrobiology is that extraterrestrial intelligent life will be very similar to us in many ways, especially when higher levels of organization are considered. This is because the processes that give rise to life are assumed to operate independently of the environment, and also because physics severely limits the variety of feasible options. Therefore, the probability that intelligent life is evolving elsewhere in the cosmos may be very high, although the probability that it is humanoid in type may be very low. The truth is that we know very little. For example, we do not know if Earth was the lucky winner of a cosmic lottery or if life has appeared elsewhere in the universe. We do not even know if a hypothetical ET would follow the same laws that we know on the only planet that definitely supports life. There is little doubt that physical and chemical laws apply throughout the universe, but there is not the same certainty about biological laws. Frankly, if we were to encounter life on another planet, we might not even be able to recognize it. In short, our first contact with advanced aliens might be a blow to our self-esteem as we face, who knows, a more intelligent species than our own. But if that first contact ever happens, we should be prepared for another twist. The aliens may be so different from us that they won't even realize that we are sentient. At first glance, trying to imagine the physical appearance of a technologically advanced extraterrestrial seems like an absurdly impossible task. For one thing, we don't even know if intelligent beings of extraterrestrial origin exist, let alone what their home planet might be or what their morphology might be. Our challenge is therefore limited to using what we know about the evolution of intelligent life on Earth, considering possible extraterrestrial planetary environments and making a series of reasonable assumptions. The two views. The disagreement about the likely appearance of intelligent extraterrestrials is divided into two opposing positions. On the one hand, some take a more anthropomorphic view of ET and believe that it would be essentially humanoid, with 2 arms, 2 legs, a head on top of the body, and the major sensory organs located on the head. On the other hand, some exobiologists believe that intelligent ET could appear in a completely exotic form because the creature would inevitably have followed an evolutionary path completely from that of humans and would have arisen in a planetary environment very different from Earth. The anthropomorphic view. Many scientists believe that aliens may not be so different from us, and to support this hypothesis, they usually cite a well-known phenomenon called Convergent Evolution. Essentially, species exposed to the same environmental pressures tend to develop similar anatomical features through natural selection. This is why a mammal like a dolphin looks similar to a cartilaginous fish like a shark. Even a creature that evolved and lived in the liquid ocean of a distant exoplanet would probably evolve a fish-like form to move quickly. After all, the laws of physics are the same here as they are on the other side of the galaxy. According to proponents of the humanoid form, speculation about ET morphology must take into account what happened here on Earth, where it was in an aquatic environment that organic matter based on carbon compounds began to develop. And it was the first marine creatures that developed the characteristic that would determine the future form of Earth's inhabitants, that of bilateral symmetry in body shape. This form, in addition to being the most economical in terms of genetic programming, minimized resistance and turbulence in the water and became the characteristic of all marine creatures, then transferred to terrestrial animals. Proponents of the humanoid form also argue that intelligence, as it is tied to the use of tools, can only arise as an evolutionary adaptation among terrestrial species. The use of tools by marine creatures would be extremely difficult due to the density and viscosity of water. Moreover, it seems likely that intelligence can only arise in predators. What about birds? Well, there are some really intelligent ones, like the crow, for example, but for an alien in the form of a bird to build tools and develop a technological type of intelligence, it would need appendages similar to ours: arms, hands, and fingers, which is obviously incompatible with an animal that uses its upper limbs to fly. Yes, because the development of legs, arms, and grasping appendages is a delicate evolutionary step on the ET's path to intelligence. Hang on a sec, guys, before we continue. Be sure to join the Insane Curiosity channel. Click on the bell. You will help us to make products of even higher quality. Primitive technology requires the ability to hold and manipulate basic tools and weapons with a certain degree of sensitivity, such as clubs, spears, knives, and tendons for bows, and the ability to combine all of this with movement speed. Otherwise, our ET runs the risk of remaining forever confined to their comfort zone and never being able to travel around the galaxy aboard a spacecraft. The issue of the number of limbs is one of the most controversial when discussing the morphology of intelligent ET. The 4 limbs we have are the product of genetic inheritance from our earliest mammalian ancestors, which was in turn inherited from fish with 4 fins that ventured onto land. But is there an optimal number of limbs? Well, a single limb would obviously be completely useless. For strictly mechanical reasons, 3 points are geometrically required to define a surface plane. 2 points form only a line. ETs trying to stand on only 1 or 2 levers will promptly fall face down. We humans can remain upright only because our large feet provide additional points of contact with the ground. But without fingers or toes, at least 3 legs are necessary. Are tripod aliens possible? Traditional biologists say no. A 3-legged creature must lift at least 1 limb off the ground, at which point it loses its planar support base, a statistically unstable and dynamically precarious situation. 4-legged creatures seem better from an engineering standpoint, since the creature can remain balanced when 1 leg is in motion. Ancestral fish only had fins in pairs, so should all limbs evolve in pairs as well? Xenobiologists are not convinced. Most running birds and quadrupeds keep 2 or fewer limbs on the ground during locomotion, so dynamic 3-point stability is probably unnecessary. Terrestrial life need not always evolve from fish, even with fins. The descendants of a starfish, for example, might have an odd number of legs. More than 4 legs are also plausible for massive, intelligent animals. Odd appendages are often used for highly specialized purposes, such as the prehensile tail of monkeys and the flexible trunk of elephants. The key to superior multipedia is neural control. The neural circuitry for an extra limb is far less than that needed to add, say, another eye. Muscles require thousands of new neurons, but eyeballs require millions. About 1/3 of the mammalian brain is devoted to sensory functions, while only a small fraction is devoted to motor control. Aliens are much more likely to have extra arms than extra eyes or ears. As we mentioned earlier, vertebrates on Earth have 4 limbs only because they share a common ancestry with 4-fin fish. Had we instead evolved from Euthacanthus, a Devonian fish with no less than 7 pairs of fins, we might be hexapods or even heptapods today. After all, there are many advantages to living on 6 legs. On high-gravity worlds, hexapods are a good way to distribute mechanical stress and reduce the risk of bone fractures. Injury or loss of a limb is more catastrophic for 4-legged humans than for 6-legged humans, who have spare limbs. Hexapods also have better balance because, unlike quadrupeds, they can maintain a stable supporting tripod on the ground even at high speeds. And it should not be too difficult to coordinate all those legs. In short, according to mainstream biologists, there seemed to be no escape from the dictatorship of the principle of evolutionary convergence. The exotic forms invoked by some astrobiologists may exist, yes, and may be the most common, but the point is that they are not evolutionarily plausible, nor can they explain how they could have achieved technological intelligence in the absence of the most basic manipulative skills. Exotic biology. However, many scientists argue that there is very little chance that an alien life form could remotely resemble us, given all the possible variables that could make a difference, such as environmental ones, referring to the particular geological, atmospheric, and meteorological conformation of the planet. Physical ones, first and foremost, the force of gravity, which is different from Earth's. Planetary ones, example, a habitable planet could have a more complex orbit and spatial geography than Earth's, and biological ones related to the evolutionary process and natural selection. One possibility often suggested by more radical exobiologists is that extraterrestrial life may depend on the chemistry that does not require the carbon atom. Although carbon chemistry is undeniably the optimal chemistry on planet Earth, one can hypothesize that biological life is built around silicon, which is very common in the sand and used specifically to make electronic circuits. This could affect the body structure of extraterrestrials, as they may require different types of proteins, enzymes, nucleic acids, and other cellular components. For example, an alien might have very thick, tough skin to protect itself from radiation, or a completely different vascular system to transport nutrients and oxygen throughout the body. In the 1960s and 70s, the famous astronomer Carl Sagan was convinced that technologically advanced species could evolve indifferently on land, sea, or air, with unimaginable chemistry, shapes, sizes, colors, appendages, and opinions. This in turn influenced the science fiction of those years, which began to imagine non-humanoid or even decidedly exotic life forms, such as sentient clouds of interstellar gas thousands of kilometers in diameter, or bizarre balloon-shaped creatures floating in Jupiter's gas belts, using a hydrogen-based metabolism instead of oxygen. Some suggest that extraterrestrial intelligent beings might resemble insects, birds, fish, or even plants. They could have a spherical shape, be sticky jellyfish-like creatures, like the heptapod beings proposed in the movie Arrivals, or even exist as a planet-sized ocean intelligence like the one in Stanislaw Lem's novel Solaris. But old-school biologists shake their heads and ask, how could these creatures have become intelligent? They seem to us to be only fanciful hypotheses, without the slightest relation to physical and biological laws. And to this, the exobiologists reply that if the goal is to scientifically hypothesize intelligent alien life forms, then it is necessary to abandon all anthropocentric preconceptions and accept creatures that differ from us in every parameter. The principle convergence is a popular one in the field of evolution, it is true, but it would hardly be able to reproduce all the physical characteristics familiar to us in creatures scattered over billions of other distant worlds. True, we won't have an answer for many years, decades, or even centuries, but it's still nice to talk about it and to anticipate issues that will affect our great-grandchildren very closely in the near future. And what do you think? Are you on the side of the old biologists or on the side of exobiologists?